So let's assign some return and risk numbers to our three assets, X, I, and J. And we will also assign a risk aversion level for our investor, and we can compute some utility levels. So let's assume asset X has an expected return of 10 and a standard deviation of 20. How much utility does an investor derive from holding this asset? Well, it depends on the investor, and remember we define the investor by risk aversion parameter A. So we're going to assume that this person has A equals 2, and so the utility derived from holding asset X is going to be the return minus the risk aversion parameter times the standard deviation squared divided by 2, or half the variance. So 10% minus 2 times 0.2 squared divided by 0.2, and this person achieves a utility number of 0.06. Now, what do we do with this? Well, we compare it to the utility from the other assets. So since asset I has an expected return of 13% and a standard deviation of 35%, then this person derives a utility equal to 13 minus 2, 0.35 squared divided by 2, of only 0.0075 for asset I. And for asset J, the expected return is 8 and 12. And remember, if we go back to our graph, we have 10, 20, 13, 35, and 8, 12. And so we have 10, 20, here we have 13, 35, and 10, 12. And these are not to scale, but, 8, 12, but these are up and to the right, down and to the left. So 1335, a utility of 0.0075, and asset J has 8 and 12, a utility of 0.60656. And so we can say that, here's a table with all the computations, that this investor, defined by A equals 2, achieves the most utility from asset J. And so this investor, faced with X versus I, would choose X because it has more utility. And this investor, faced with X versus J, would choose J because it has more utility. And again, this is ordinal, not cardinal, or just the order of this. 0.0656 is greater than 0.06, so therefore J is better than X. And 0.06 is bigger than 0.0075, so X is better than I. But we can't say that the degree to which J is better than X is more than the degree to which X is better than I. Again, it's just the ordering of these things. Let's draw the indifference curve. It's also called an iso-utility curve. What that means is for each point on the curve, an investor will have equivalent utilities. So this is very important. Not every spot on the indifference curve is available. Sometimes only one point on the iso-utility or indifference curve is available. The curve shows other investments that would provide the same utility to the investor if they were available, but they are not necessarily available. We're just drawing this theoretical curve so that we can compare investments. So what we want to do is we want to rearrange the utility equation to make it easier to graph. Since expected return is on the y-axis of our graph and standard deviation, or sigma, is on the x-axis, we'll rearrange this utility function into this form. We'll bring expected return over here, we'll bring utility over here. And what we have is that the expected return is equal to A, the risk aversion parameter, times the risk squared divided by 2 plus U. And so for any individual with risk aversion A, I can plug in a sigma and spit out an expected return for any constant utility. And so this can show me how expected return has to increase as risk increases to maintain this same level of utility. Now let's just look at the basic form of this equation so we can understand how to graph it. And I can see that this is of the same form as y equals A times x squared plus b. And I can see that this is a parabola that has a slope of A and an intercept of B. It's really half a parabola because the domain of my function must be standard deviation, and standard deviation must be positive. So it's just the right half of a parabola, but it's the right half of a parabola with slope A and intercept, that should be U. And so for A equals 2, for any given sigma, we can determine the expected return. And so every point on the line above provides the identical utility for a person with risk aversion to A equal to 2. So what does the ISO utility look like for different levels of A? Well, a person that is more risk averse, that has a risk aversion level equal to 4, I know that this is going to be a steeper parabola because I'm multiplying the sigma times 4. And so I can see that for A equals 4, it's steeper than A equals 2. And the way to think about this is if I'm going to have some sort of risk increase, well, then this person needs a little bit more return, but this person needs a lot more return because they are more adverse to risk. And so to incur more risk, this person needs a little more return, this person needs a lot more return. And so the steepness of this parabola is a function of the level of risk aversion, and this makes intuitive sense. The person with greater risk aversion requires a greater increase in return if they are required to incur more risk. So now for a person with a given risk aversion level, A, we can select between assets X and asset I and asset X and asset J. We can do this graphically. We did it before numerically by computing utility, but now we can graph this using the ISO utility curve. So here's asset X, I, and J. Let's consider the ISO utility curve for a person with a risk aversion level equal to 2. For A equals 2, asset X is in their investment opportunity set, and so we'll draw a correctly sloped ISO utility curve through asset X to determine all other investments that would provide the same utility as asset X. And here I have the curve the curve that runs through asset X, but I can compare it to asset I and I can compare it to asset J. And I can see fairly easily that X is better than I, but X is worse than J. Let's talk about how. So what I've done is I've just drawn this again, but I've added 2 extra dots on the ISO utility curve. Both the blue dot and the red dot lie on asset X's ISO utility curve for an investor with A equals 2. Therefore, both the blue dot and the red dot, if they were available, would have equivalent utility to asset X. Note that the blue dot and the red dot are not available investments. We cannot invest in the blue dot and the red dot, but they are important because we can use them to easily see dominance relative to asset I and asset J. So compare asset X to asset I. I can see the blue dot dominates asset I. It's to the left. Or if I drew it up here, it would be above. And so for identical risk, for identical return, it has less risk, or for identical risk, it would have greater return. And so equivalent return and lower risk. Therefore, since X is equivalent to the blue dot and the blue dot dominates I, X dominates I. And similarly, I can compare X to J because I can see that J dominates the red dot. And it has equivalent risk but greater return. Or if I put the red dot here, which I could do, I could see that it has equivalent return but less risk. And so since X is equivalent to the red dot and J dominates the red dot, asset J dominates X.